All right, welcome everyone. This is the start of my video lectures for Physics 110 because we have to stay at home now. So let's go ahead and look at, last class we worked a lot on equilibrium situations, and we also looked a lot at how to make free body diagrams, how to analyze the situation. So the first thing I have here is what I'm going to call example 0, which is just kind of a recap of the things we learned before. So the scenario that we have here is that Iris drags a sled containing her baby brother across the floor at a constant speed. She pulls the sled at a 20-degree angle above the horizontal. We want to do a free body diagram and write out Newton's second law for both the x and y directions. So there's nothing to solve here, just to be clear about that. All we want to do is identify the forces that are acting on our object and the x and y directions. So the first thing to consider here is, what is the object? So I am going to choose, for this example, to treat the sled as the object. So once you identify what your object is, you then start talking about what the environment is. So if the sled is the object, that means the environment is going to be the baby brother that sits on top of the sled, and it's going to be the ground that is supporting the sled, and it will also be the rope that is pulling the sled along. So every time you start your problems, it's really clear to be aware of what the objects are and what the environments are. So let me jump ahead to my worked out example here. All right, so here's, so if you look on the left-hand side there, we have our object, which is the sled, and we have the environment, which is, again, brother, floor, rope, and technically the earth, because, the gravity's there, so gravity does obviously count as that. So we got to think about all of the ways that the environment's going to act in the object. And again, if things are not clear here, you may want to do a force identification diagram, have the sled circled, and then you can see all the things that are in contact with the sled. Again, baby brother, floor, rope is all in contact with the sled. We have one long-range force, which is the earth. Okay. Which is gravity from the earth. Okay, so if we look at the free body diagram that I drew here, obviously, good thing to start with is gravity. Gravity is going to be downward. I chose that length to be somewhat arbitrary, but that is going to be the weight of the sled. Okay, there is a normal force from the floor pushing upward, so I've labeled that NF. So it's normal force from the floor pushing upward, and then the baby brother who sits on top is going to exert a normal force downward. And so I've indicated an arrow there. And so if you notice that the arrow for FG and the arrow for N sub B, which is the normal force on the brother, when you combine those lengths together, it's pretty close to what the length of NF is. And that's important because we have an equilibrium in the y direction. In fact, it's not the only force we have in the y direction. If you see, I have tension drawn here. And so tension is at this 20-degree angle. So the tension actually serves a couple purposes here. It is mostly intended on pulling the sled across the floor, but there is a component that goes upward, and what that does is it acts to support the sled to some extent against the weight of things that are on it. So in terms of what's going on in the y direction, you can see the second equation that I have here is NF is up, T sine 20 is up. So that is the vertical component of tension that is upward, and that is balanced by N sub B and FG. So we don't have a situation of acceleration here. Everything is going to be what we consider a dynamic equilibrium. And so two forces up, two forces down. Make sure you make the forces that are down negative, and that's our Fy equation here. All right, so what's going on in the x direction? Well, I already have my tension there, so I know the tension has a component that would be given by the cosine that will be responsible for pushing this thing to the right, overcoming gravity. And the leftward forces are actually going to be two frictions. Okay, one is with the ground, and that force from the ground is going to be supplying a kinetic friction because the the ground surface and the sled are moving relative to each other. That's definitely a kinetic frictional force. And then there's a static frictional force that's between the baby brother and the sled. Now, the baby brother and the sled do not move relative to each other. And in fact, the sled is going to be responsible for pushing the baby brother along. And so there has to be a backwards force from the baby brother on that. And so we have a t cosine 20 for our x direction, and we got the two frictional forces that point to the left. And that's our Newton's second law. So one thing that was maybe not entirely clear excuse me, in this problem here, and it's actually a big topic of what we're going to work on today, is Newton's third law. So if you consider what's going on with the baby brother, right? Think about the forces on the baby brother. We have gravity down, we have normal force upward, and something propels the baby in the x direction, and that's a static frictional force. So you may remember we had a couple static frictional forces when we worked out free body diagrams in one of the previous homeworks. Well, according to Newton's third law, if there's a normal force up and a frictional force to the right, there needs to be similar, equal, and opposite forces that act on the thing that it is in contact with, and that's with the sled. So that's how we'll know this. And again, we'll be working this out as we move along through this lecture here. But in total, we have what appears to be 6 forces. And again, if it's not entirely clear how all the forces work out here, you may want to do a force identification diagram and be sure that these are all the forces that work. But all right, let's move on from this next example. All right, so again, the main focus for today's lecture is on Newton's third law. And Newton's third law at its core is all about interactions. We have an object that we're interested in, and there's an environment that acts on it, and we want to understand how those interactions take place. So we've seen lots of interactions before. There's all kinds of things you can point to. The picture showing a bat and a ball. So what happens is the bat exerts a force on the ball exerts a force on the bat. If you're probably sitting in a chair right now listening to this lecture, and if that's the case, then you have gravity pushing down. The earth pushes back up on you. There are normal forces on you, so you're probably pushing on the chair pushes back up on you. So all of these things that we identify here are pairs. That's how interactions take place. They take place with pairs, and we call these things action-reaction pairs. And so there's obviously an agent and an environment, and so every time you have these pairs, we're considering how those interactions are taking place. So let's specifically talk what Newton's third law is. And so, if you look at the bottom here, there's sort of a catchy phrase that describes Newton's third law, which personally I find to be kind of abhorrent. It's, at best, it's just a gross mischaracterization of how Newton's third law works, and that's for every action, there's an equal and opposite reaction. And that's a pretty horrendous way to state Newton's third law because it oversimplifies things so much so that I think it would cause a lot of confusion with a physics student. I mean, it sounds nice if you're just a person listening to somebody talk. It's like, okay, well, equal opposite reaction, great. But if you're a physics student, you're going to want a better description of this. So what I have listed here is really the best way to describe things. So let's just go through each point here. Every force occurs as one part of an interaction pair. Okay, so that means no force exists by itself. No force exists by itself. There's always a second force that can go with it that has a particular nature to it. These two forces, this pair, are called an action-reaction pair, and these things act on two different objects, the objects that are a part of the interaction. The two members of this action-reaction pair are the same in nature, equal in magnitude, opposite in direction. Okay, so when I say same in nature, I mean this. If one's a gravitational force, the other one's a gravitational force. If one's a normal force, the other one's normal force. If one's friction, the other one's friction. That's what we mean by same in nature. Equal in magnitude sounds exactly how it sounds. Numerically, they're the same. Opposite in direction, and that's indicated by the equation here. We see that we have f of a on b equals to minus f of b on a. So the way you read that is this. F, so on the left-hand side, is the force of A exerted on B. That means B is the object and A is the agent in this situation. And that is equal to F of B on minus F of B on A. So in this case, A is the object and B is the agent. Okay, so this is a vector equation. The magnitudes are the same. The negative sign means opposite in direction. Okay, so what this means is we actually have two free body diagrams here. We have a free body diagram for B, and we have a free body diagram for A. Okay, in the free body diagram for B, we will see F of A on B, and in the free body diagram for A, we will see F of B on A. Okay, Newton's third law interaction pairs never occur in the same free body diagram. That cannot take place. Okay, so here's a good example of these two boxes or something here that are interacting with each other, and they exert equal and opposite forces. This is some kind of contact force. You could describe this as a normal force, but these things are definitely part of the interacting pair. Okay, so just like I do in lecture, I'm going to have a series of questions for you that are going to go over how these interactions are going to take place. So in this example here, car B is stopped for a red light. Car A, which has the same mass as car B, doesn't see the red light and runs into the back of car B, and we're trying to figure out which of the following statements are true. So if you consider that for a moment, you can pause the video if you need to, but the answer here will be C. Okay, so car B, the one that is stationary, is going to exert the same amount of force that A exerts on B, okay, which I wouldn't say is counterintuitive, but I have, in my experience, seen a lot of examples where students look at the situation and think, well, A is going to hit B, right? So A is hitting B harder and B stationary, so it can't hit back on A as much. But that's not what Newton's third law is. Newton's third law is if there is a force, there is a second force, equal and opposite. So the answer definitely is C here. All right. A small car is pushing a larger truck that has a dead battery. The mass of the truck is larger than the mass of the car. Which of the following statements are true? Again, think about this for a moment. You can pause the video if you like. But the answer here is going to be C. The car exerts the same amount of force on the truck as the truck exerts on the car. Why? Because Newton's third law. Okay. Now, when people read this, though, there is something that kind of gets people stuck. And that's this idea that, well, if the car and the truck push on each other, right, because the car is pushing the truck forward, and that means the truck is pushing back on the car. So one question you could ask yourself was, well, how are things even moving then? If things are pushing back and forth on each other equally, I don't see how anything can move. And the problem with that kind of thinking is that it's not object-centric. Like, you have to really look at a single object and you ask yourself what is going on with that object. If you have interactions, that's fine, but you need to deal with the two interactions completely separately. You have to look at the car separately, then you look at the truck. Okay, so let's consider what's going on with the car. So the car has a force on it from the truck that pushes backwards. Okay, now the picture is indicating that there's an acceleration. So if there truly is an acceleration here, there must be a forward force that would be probably static friction from the tires on the ground that are pushing the car forward. And if you could see the free body diagram of this, you would see that the push forward is larger than the push back from the truck, and that's why the acceleration takes place. Likewise, if you look at this truck here, a free body diagram of the truck is going to show the push from the car and probably some kind of backwards force that's some type of friction, but the forward force is going to be larger than the backwards force, so the truck accelerates. The fact that the two objects share equal and opposite forces is really of no consequence because you need to consider the other forces that are in the environment. You look at a single object and you analyze what's happening to that one object. Okay. The only thing that Newton's third law helps you to do here is that when you want to look at both free body diagrams, you can make a connection with one of those forces that says they're the same. All right, let's keep going. All right, a car is parked at rest on a horizontal road. The upward force of the road on the car, normal force, is the same as the downward pull of gravity. Okay, this seems simple enough, right? So think about this for a moment, or a second, and vote. Well, actually, you're not voting because you're watching this by yourself, probably. Anyway, so the answer is B. Okay, so what's going on here? Well, this is not Newton's third law. So if you look at A here, because they're an action-reaction pair, no. Because Newton's third law has an aspect to it that says they must be equal in nature. Okay, we're dealing with a normal force and a pull of gravity. Those are not the same in nature. So if there's an upward normal force on the car from the road, that must mean that if you look at the road, there's a downward force from the car. All right? Same thing with gravity, right? If you look at the car, there's a downward pull of gravity. So that means if you look at the earth, there's an upward pull from gravity. And those are the action-reaction pairs. This car is at rest because it's obeying Newton's first law. Object at rest will stay at rest unless acted on by an external force. And so if there's no external forces, if there's no F net, then the object's at rest. And you don't need to explain that. It's just, that's the way it is. All right, so let's start looking more at these interactions. I mentioned gravity. So long-range forces obviously obey this as well. If we have gravity involved, there must be pairs. So if the Earth exerts a force on the moon exerts a force back on Earth, they're equal. Okay? If you have a gravitational force on you, which I hope you do, that means that you're exerting a force on the Earth. Okay? Equal, opposite, and the forces are exactly the same. All right? So, well, actually, you know what? Let's go back to that for a minute here. Actually, there's one thing I want to mention. In fact, you know, maybe I don't want to get ahead of myself here, but I got a point, and I want to make sure this point's going to be made at some point. I don't know when it's going to be made. Well, actually, maybe it's down there. I don't know. Okay, I'm just going to say it now, and if I'm going to say it a second time, oh well. All right, so let me talk about this thing here. And this is actually something I ask my astronomy classes a lot, too, because they got to understand a little bit of physics. But, you know, when you tell people this, I get a lot of people in my astronomy class saying, you know what? I don't know about this, because the Earth obviously has a pretty large impact on things, right? You can see the impact. You throw an object in the air and it falls down, right? So, you know, you don't see the gravitational impact of small objects. And so you think, well, something's not right here. And, you know, I sort of agree with that. Something definitely is not quite right here. And the reason why things don't seem quite right is because of your misunderstanding of how you experience the world, okay? So when we say equal and opposite forces, well, you know, you certainly don't feel that's the case, okay? It's hard to convince somebody that, oh, yeah, you have a gravitational force in the Earth, and it's completely identical to the gravitational force that the Earth exerts on you. It doesn't seem that way, and my simple answer for that is because you don't experience forces. You don't have the means to do that. There's no way for you to know that forces are equal at all. So, you know, you look at a situation where I'm going to jump off this large cliff here, right? You jump off a large cliff, gravity's going to accelerate you downward, you're going to hit the ground and have a bad day. And for the most part, you know, the Earth is pretty okay. So what's different there? Well, Newton's third law says that the forces are completely identical, and they are. But what are you experiencing when you jump off the cliff? Are you experiencing a force? No, you're experiencing motion. You experience velocities. That's what you feel. You feel accelerations. You feel changes in velocity. So what happens if you look at the situation where you have the force and you exert forces on each other, the Earth and you exert forces on each other, then you have to look at Newton's second law and realize that, okay, F equals F, right? Well, that means MA equals MA. Okay, so then when you're looking at those quantities, the masses are radically different, right? The mass of the Earth and the mass of you, totally different, right? You have a tiny little mass. So how do you make the force the same? Well, the product of mass and acceleration is what makes the force the same. So guess what? You have a tiny little mass, and that means your acceleration is quite large. And the Earth has an enormous mass, and so its acceleration is tiny. I mean, technically speaking, if you jump into the air, okay, the Earth is accelerating you downward, and you are accelerating the Earth upward. But because the mass of the Earth is so enormous, it's immeasurable, your effect on the Earth. So that's why it seems different. And you really have to think about what the accelerations are. And the accelerations are based on mass. And that's what you experience. All right, so let's talk about analyzing systems now. So as I've sort of mentioned several times already, we are very interested in our system, which includes an object and an environment. Okay, so what's being indicated in the picture here is what I'm going to refer to as an interaction diagram. And the interaction diagrams are what helps you organize objects and environment and interaction. So this is very similar to having a motion diagram. It's very similar to having a force identification diagram. This is a tool that I hope you can utilize to get you to understand interactions. And again, this is not something that will be necessary for everything unless I tell you to do it, then you got to do it. But it's a tool that can help you understand interactions if you need it, you know. So in this example here, we have our objects here. We have two objects here, okay? We have object A and object B. And that means we would have a free body diagram for A and a free body diagram for B. C is going to represent our environment here. And as you can see with the lines that are drawn here, C is interacting with A and B. Okay, so an example of this could be, C could be the ground, for example. And the lines that connect A and B might be normal forces that are exerted on A and B. Now, if you look at A and B, there are two lines drawn between them. So that means there are two Newton third law interacting pairs between them. Okay, and who knows what those could be? I mean, one can be, I don't know, like a type of normal force, and one can be like a friction or something like that. It's this sort of a vague example here, but this is showing the interaction. If you look at A, there are three lines that touch it. There are three forces in its free body diagram. If you look at B, there are three lines that touch it. There would be three forces in B's free body diagram. C is part of the environment. You would not make a free body diagram for C. All right. Well, look at this. I just said all this stuff. Yeah. All right, move on. All right, so this shows a little more precisely what we're talking about here. We got a box around our system. A and B is the system. Again, A and B have free body diagrams. C is the environment. Those are external forces. When we look at our situation, we're going to create a diagram like this. We call it an interaction diagram. All right, so we got a man here pushes a crate across a rough floor at a constant speed. So he's trying to exert his dominance over an inanimate object here. So we want to have an interaction diagram here. We want to see how this guy and this block or whatever this thing is here is going to interact. So we want to have free body diagrams for each object, and we want to connect any Newton third law interacting pairs. So let's see what happens here. Where is this? All right, so I'm going to start off with my interaction diagram. So pay attention to the left side there. We have our system. We got a person, we got a box. All right. Now, the environment is everything that is in contact with the things in the system. So the only things that are in contact with the system is the floor and the earth. And so below that, I have put my interaction diagram. And here's the order at which you should do things. You want to indicate all the objects in your system. So if you identify two objects in your system, you are going to put two circles in your large box here. So I have P for person, B for box. I do circles around them. And I first want to think about what kind of forces are exerted between them. So the guy is pushing on the box pushes back in the guy, and so I'm going to call that F push. So I'm going to draw one line between P and B to indicate that interaction. All right, well, the only point of contact between the person and the box is, this push here. So there really isn't any other interaction. I mean, there certainly can be more interactions than this, but there's just not. So, and then what's the environment? So the environment's the floor and the earth, which I labeled F and E. And so I have F, a circle underneath that, have E as a circle underneath that. And then you draw lines from your objects to the system based on how the interactions are going to be. So both the person and the box have a gravitational force. So you see there are lines drawn from P and B down to E. And I labeled them FG. Great. With the floor, there actually are going to be two interactions that takes place here. Okay, now for the person's pushing on the box, and so what happens is, their feet do not move relative to the ground. If they did, they wouldn't be pushing the box very well, and they'd be doing a bad job of that. So there's a static frictional force that's exerted on the ground that allows the person to push the box forward. There's also a normal force, so I've labeled those, as you can see down here, F, S, and M. When I look at the box, I see that there are two interactions there, N and F sub K. So the box does move relative to the ground. It is dragged across the ground. That is a kinetic frictional force. And of course, the ground exerts an upward normal force. All right, so it appears I've identified correctly all my system, all my environment. I've connected all the forces that I believed are acting on things. So this helps me organize things nicely. The one thing that's really nice about these diagrams is look at P. How many lines touch P? 4. That means there's 4 forces in the free body diagram. If you look at B, again, 4 lines touch it. That means 4 forces in its free body diagram. So then we move to the free body diagrams. Okay, free body diagram of person. I drew a coordinate system. I label X. I label Y. I got friction. Not friction. I got gravity downward. Now I labeled it FG. It actually would probably be wise to label this like probably FG sub P, just to be really clear that I'm indicating the gravitational force of the person. So I really ought to have like a different notation for F sub G and N actually. N should probably have N sub P on it to indicate it's the normal force exerted on the person. But there's an equilibrium in Y, so I want to make sure I draw the normal force just as high as I draw the gravity force going down. All right, great. Now, static frictional force is going forward. That's propelling the person. That allows them to push the box. And then they have the push on the box, and I'm labeling it FB on P. Again, that means the force of the box on the person. This is the box pushing back as a result of the person pushing forward. And again, those vectors are equal because everything is constant speed here. Let's move to the box. Okay, gravity down, normal force up. Vectors equal, as I mentioned before, might be wise to include subscripts here. F, G sub B, N sub B, okay? There's a kinetic frictional force pointing to the left because the box is being dragged to the right. And then we have F of P on B. This is the person pushing on the box. So again, it's force of person on the box. And those two forces, the kinetic friction and the push, are equal because it's constant speed. And there is one interaction here. You draw a little dashed line between the F P on B and the F B on P to indicate a Newton's third law interacting pair. So if you go back to your interaction diagram here, there's one line that connects B and P. That means there is one interaction pair, and I've indicated that by drawing this little dashed line. And so that is a complete analysis of what's going on physically with the person in the box. So you got your interaction diagram. Again, it's optional unless I say, hey, you got to do it. And then for the person in the box, you got the free body diagrams. Now, if we were given numbers and other information, then we can solve for some unknown variable. I don't know what that is, but you can, if you have numbers, you can do that. So, all right. And let's keep going, I guess. All right. So this one's a great. What we have is we have two strong magnets are on opposite sides of a small table. Magnetism keeps the lower magnet from falling. Draw an interaction diagram for the system. Draw free body diagrams of each object connect Newton's third law, interact in pairs. Okay, so one thing to keep mindful of here is that, for the most part, we've always had one long-range force, and it's gravity. But here we have magnetism, and that's really the only other long-range force that we would ever consider in the physics classes that we have at this level. So, so we have to just realize that for magnetism, we don't have to have things in contact. The lower and the upper magnet are going to be interacting with each other. And because of the attraction there, they're going to be sort of squeezing on the table. So because they're in contact with the table, we're going to be looking at normal forces that are exerted. All right, so let's go ahead and look at how that's going to go. All right, so start on the left here. We have our interaction diagram, and we have our system. Our system consists of three objects: the upper magnet, the lower magnet, and the table. And the environment are all the things that are in contact with the parts of the system, and that's the floor and the earth. All right. So we're going to draw three circles: upper magnet, table, lower magnet, indicate the system. The upper and lower magnets are exerting a force on each other. I'm going to label that F. That's called the magnetic force. There's normal forces exerted between upper magnet and table and lower magnet. So that takes care of the interactions that are going to take place with the things in our system. And now we got to look at the environment. So we have Earth, and all three objects are attracted to the Earth. So we got lines going from all three objects down to the Earth, and the floor is in contact with just the table. All right, so let's go ahead and look at you. See that there are three lines touching it. Our free body diagram is going to have three forces in it. So let's look at the free body diagram of the upper magnet. Now, just to be aware that there's so many forces here, and there's so many really subtle interactions that I did not attempt to draw the vector lengths to scale. So I normally don't like to do that, but it's very difficult to sort of manage all that, especially when you don't have numbers. So when you look at these, just sort of consider their directions and sort of relative magnitudes within the free body diagram, okay? So we got gravity going down, obviously, on the upper magnet, and we have the magnetic force pulling downward, right? So the lower magnet is attracting the upper magnet, so it pulls it down. The table exerts an upward force on the upper magnet, and what that does is it supports that object against two things: the gravitational force that's pulling down and the magnetic force that pulls down. So the normal force is going to be higher than gravity because it's also accounting for the magnetic force. All right, so if we look at the lower magnet, again, we have three forces. We have three lines that touch that, so it's going to be three forces that are going to be in our free body diagram for the lower magnet. So let's go on the right here and look at that. We have gravity going down as always. We have the upward magnetic force from the upper magnet. So that pushes up. And then because we're in contact with the table, the surface is above the magnet. That means the normal force is going to be directed downward. And so the sum of the normal force downward and gravity are going to be equal to the magnetic force that's up. All right, so that's all settled. The table, as you can see in the interaction diagram, has four lines that touch it. There are four forces. You can see there are three of them are normal forces, actually. So we have the table's gravitational force is downward. Great. Okay. We have both the upper and lower magnets providing that sort of push, that sandwich interaction. So that means the lower magnet pushes up on the table, the upper magnet pushes down on the table, and of course the floor pushes up on the table. So the sum of all those forces, of course, is zero as well. And then we have three interaction pairs. So if you see, I have these dashed lines that connect the normal force from table and upper magnet. We have a dashed line that is the normal force of lower magnet on table. And then we have the magnetic force on the upper and lower magnets. And so that is the complete analysis of this system here. So what I recommend you do is when you look at this, rewind the video and watch it about 10 more times. And hopefully after about 4 times you get it, and then 6 more times for good measure. How about that? But, really go over this, though. And if anything is completely unclear about this, then post either send me an email or post it in the discussion thread that I'm going to have for this video on Canvas. But this is probably the most crucial example. If you really get this one, I think you really understand interactions very well. So definitely spend some time going over this a bit. Let's get back to the lecture. All right, so we have a question now. And it says, what, if anything, is wrong with the force diagram for a bicycle that is accelerating to the right? All right, so let's look at the picture here and see if we can make sense of this. What do we got? We got on the person, they're showing three forces, something upward, something downward, something to the right. Okay. They're showing a surface, they're showing the earth. Looks like the earth has got an upward force on it. Looks like the surface has a left and a downward force on it. And all the dashed lines indicate interaction pairs. So think about this question for a moment. All right, you might want to pause the video. But the answer here is B. So one big problem with this diagram is that when you look at the bicycle's free body diagram here, these aren't really proper free body diagrams, but we'd consider them force identification diagrams. But there's a dashed line that connects the upward and downward forces on the bicycle. And so there's a problem with that. And the problem is that you can never connect Newton's third law interacting pairs within a free body diagram. That upward force that we see on the bicycle's free body diagram is likely a normal force. So it actually should connect with a downward force on the surface. And so that's not really being illustrated here. We have a forward force that's probably static friction from the wheels on the ground, and we have a downward force that looks like it's probably gravity. That should be connected to the upward force that we see on the Earth. The one thing that is definitely right here is that the forward force of static friction is connected to a backwards force on the surface. That's correct. The other interaction pairs are not labeled correctly. The one at the top and the one near the bottom are not correct interaction pairs. Just to go over that one more time, the bottom interaction pair between the surface and the earth, well, first of all, our object would be the bicycle here, so we would never consider interaction pairs between environment stuff. But anyway, the upward force appears to be probably gravity, and the downward force is definitely a normal force. So those are not equal in nature. That would not work. On the bicycle, again, normal force, gravity, they're different. So, the line should connect differently there. Okay. All right. In fact, this is actually the question I was discussing earlier here. So anyway, mosquito runs head-on to a truck, which is the following is true. Okay, so look over those and tell me what you think is correct. The answer here is C, and it's because of Newton's third law. Same force, that's always true. By the way, if there's any question asks you, is the force different for an interaction, and you say no, well, wait, hold on. If the force is the same, you say yes, whatever. Yeah, okay. Mosquito runs head-on to a truck, what is true? So now this is not about forces now, this is about acceleration. So you remember what I said earlier in the video? So think about this question for a minute. The answer is A. All right, so accelerations are different. Forces are the same, accelerations are different because of a mass difference. Okay, mosquito is going in one direction, truck hits it, and then it immediately changes direction and it's going the opposite way. And the acceleration of the mosquito is enormous because the mass is so small. The truck, on the other hand, has an enormous mass and experiences an extremely small acceleration. It's negligible, basically. But it's because of the mass difference. Mass difference results in an acceleration difference. And again, that's what we experience. That's what's going on here. All right, so here's another good example here. We have blocks of different masses. They're all lined up on a frictionless table. All three are pushed forward by a 12 Newton force. We want to know what the acceleration of the system is, and then the individual forces between blocks. Okay, so this example is different because we're now not only going to analyze what the forces are, but now we have numbers behind it, and we can start to plug in numbers to things. So let's go look at how that example is going to go. All right. So if you look at near the top there, I showed we have 3 blocks all together. And the 12 Newton force is going to push on the 1 kilogram block, and it will move the entire system to the right. All right, so the first thing I'm going to do here is I'm going to look at the free body diagram of block 1. And so you see that on the left there, we have gravity going down, normal force going up. Now, I didn't label the normal forces of gravity differently because for all 3 blocks here, they are equal to each other and they're not going to be incorporated in any of the math that we do here. So I didn't choose to label them in the free body diagram. So really what you're looking at here is what's going on in the x direction. Now, for completeness, I've included the normal forces and gravity in the y direction, but they're all, F net equals 0 for those directions. All right, block 1, we got the 12 Newton force pushing to the left, and block 2 pushes back on block 1. Okay, but you want to draw the 12 Newton vector larger because this system is accelerating. So if I had to write out Newton's second law, as you can see at the bottom there, 12 newtons minus F2 on 1 is going to equal the mass of block 1 times its acceleration. All right, let's move to block 2. Normal force up, gravity down. To the right is the push by block 1 on 2. What pushes back is block's 3 response on 2. And again, the force of 1 and 2 must be larger because the entire system accelerates. So if you look below that, our Newton's second law is F1 on 2 minus F3 on 2. Notice that all these forces end with on 2. 2 is the object. Whatever is before the on are the agents, right? They're the interactions. And that equals the mass of block 2 times its acceleration, right? Now we move to block 3. Normal force up, gravity down, and we only have a normal force pushing forward. That is 2 on 3, okay? Now, I didn't label it here, but there is a couple of Newton third law interacting pairs. F of 2 on 1 is the interaction pair with 1 on 2, and F of 3 on 2 is the interaction pair with 2 on 3. So F of 2 on 3 is going to be equal to the mass of the third block times the acceleration. And so this is a system of equations here. You got 3 equations. We effectively have 3 unknowns. The system is solvable. But however, there is a much easier way to solve the whole thing. And let me explain that to you. So if you consider the 12 Newton force is pushing a 6 kilogram system. Okay, now in this problem, we have identified a 1 kilogram, 2 kilogram, 3 kilogram block. We don't necessarily have to do that. We can just say, well, there's a 12 Newton force pushing all 3. So if a 12 Newton force pushes 6 kilograms, that will produce an acceleration of 2 meters per second, was what you see on the right here. Okay, we know that all 3 blocks must have the same acceleration. If they did not have the same acceleration, then the blocks would move differently and they wouldn't be in contact. All right, so we know that all the accelerations are the same. So that allows you to really do this much more efficiently if we say, okay, we got a 2 meters per second squared acceleration. So we go to the Newton's second law for 3, and we know the mass is 3, the acceleration is 2, so the force of 2 on 3 is 6. By Newton's third law, 2 on 3 is also 6. All right. Let's look at the free body diagram for 1. We got 12 minus, well, we don't know that F of 1 on 2, but we know that the first block has a mass of 1 and the acceleration is 2. So the right-hand side of the equation is a 2. 12 minus something equals 2. That means F of 1 on 2 must be 10, and therefore F of 2 on 1 and is equal to F of 1 on 2. Everything is 10 there. All right, so this problem makes a lot of sense when you think about it like this. You need 12 newtons to push 6 kilograms, right? The interaction between 1 and 2 has gone down to 10 because 10 needs to push 5. Great. Then we look at between 2 and 3. We're only pushing a 3 kilogram mass. We only need 6 newtons to push a 3 kilogram mass at 2 meters per second squared. So the force, the magnitude of the forces are decreasing as we move through the blocks. You go from 12 to 10 to 6. And that's a pretty good analysis of what's going on in the system here. All right, so let's move on to the last parts of the lecture here. All right, so now conceptual question based on what you learned here. Okay, blocks A and B are sliding to the right. We got a hand that steps in the way, and the hand is attempting to slow them down. We know that the mass of A is larger than B. We want to rank in order from largest to smallest the horizontal forces on A, B, and H. So spend a good time looking over this. You may want to pause the video and just really ponder what's going on here. But I will tell you that the answer here is B. Okay, so what's going on here? Well, the hand is trying to stop 2 blocks, right? So that means the force on the hand must be the largest. Of course, the force on the hand, due to Newton's third law, is going to have to be equal to the force of the hand on B. So F of B on H, F of H on B are equal due to Newton's third law. The hand is trying to stop both blocks, so the magnitude of that force is going to be larger. Then we look at the interaction between A and B. Okay, now B is trying to stop A, but A has a lower mass than the entire AB system, so we would expect the magnitude of force on it to be less, and it is. F of A on B is less than the hand's force, and so we have that inequality here. So the interaction between B and H, bigger. The interaction between A and B, less. All right, good. Oh, look at that, I'm done. Okay, so I don't want to finish up quite yet here. So again, if you have any questions about the things in this video, I'm going to have a discussion thread in Canvas where you can post questions and I can respond to them. Of course, you can certainly send me a direct email. I would prefer you put things in the discussion because likely the question that you have will be questions that other people have, and it would be nice to see what they have to say. What I want to do before this video is over with, I do want to go over the homework. This is the homework that was assigned when we were still on campus. And so I just want to make sure I go over this and make sure you understand everything that's happening here. Situation number 1 here is a static equilibrium. And the ring is the object here. And you're going to have 3 forces. You're going to have the tension from the rope 2, tension from rope 1. And then you're going to have this 100 Newton force that's down at this angle here. You won't consider gravity. You're not given a mass, so you don't have to worry about that. 2 and 3, these are both situations where you have the masses. So the free body diagrams are basically done for you. It's a matter of just creating components and trying to add them up. If they add up to 0 or close to 0, then you can say it's 0. Like for example, in the one on the right here, the forces along the y direction are intended to be canceled out. So yeah. Anyway, for 4 and 5 though, 4 or 5 and 6, you definitely want to show free body diagrams for these. And you want to have free body diagrams for every possible situation. And there's in number 4 there is rest, steady speed. Now rest and steady speed, they're the same free body diagram. There's no difference between rest and steady speed. There's a separate free body diagram if you speed up and a separate one if you slow down. So you want to have free body diagrams for all 3 scenarios. You write out Newton's second law, and you want to solve for the tension in all those. For number 5, again, every time the motion changes. So the weight before the elevator starts moving, there's a free body diagram for that. Passenger weight while it's moving up, there's a free body diagram for that. And for part C, weight after the elevator reaches cruising speed, well, that really should be the same as A, so you don't necessarily have to have a different free body diagram for that, but if you did, great for you. So do that. Number 6 is static equilibrium problem. Very similar to number 1 up here, but again, free body diagram, write out the components. All right. Let's look at the new homework though, which is somewhere. I don't know where it is. Where is this homework? Oh, here it is. Okay. So ignore these dates here. I don't know what the dates are going to be. I'll post it to the webpage and I'll tell you what they're going to be. But if you notice for problems 1 to 5, interaction diagrams, free body diagrams, connect through Newton's third law, interact in pairs. Okay, I was very clear about what objects you got to do here. Okay, so 2 objects here. Number 2 has 3 objects, then 2 objects, then 2 objects. Okay, so interaction diagram, free body diagram for every object, connect Newton's third law interact in pairs. There's no numbers on any of those problems, so you're just drawing out those diagrams. And then you got 2 problems that do have numbers on it. Okay, so this is number 6 is a straightforward force thing. Free body diagram for each of the 2 objects that we're interested in, which apparently is the ice and the rope. So do that. For number 7, we got an astronaut. All right, and so we push off a satellite. This is a basic Newton's third law interaction pair stuff. We want to know how far apart the astronauts after 1 minute. So what that means is you're going to solve a force thing, and then you're going to move into kinematics and solve a kinematic thing. Okay. Basically, what you'll do is you'll work out an acceleration. The acceleration occurs for half a second. That will make the astronaut and the satellite accelerate for that half second. They will reach a top speed, and then after that, they coast for a minute. So that's what you want to figure out. Okay, I believe that's it. So stay safe. Have a nice day.